Margarita, are you seeing the appropriate thing?
Yes, I am.
Awesome. Okay, great. So, and you're welcome. Yeah. So anyways, I'm going to talk to you today about how can cognitive science research help improve education, and focus in on the case of comparing multiple strategies to improve mathematics learning and teaching. This work's been done in close collaboration with John Starr, Kelly Durkin, and Abby Lair. And oops, just a second, it did not advance. There we go. And just as a background, so a lot of my talk today can also be found in this new Current Directions in Psychological Science article that just came out. So if you want to dig into more. And I'm going to take a minute at this high level before diving in. When we think about cognitive science research, and here I am talking with a bunch of fellow awesome cognitive science researchers, and I think we all agree that there are lots of insights into potential ways to improve teaching and learning in schools from our research, but also that those insights infrequently make their way into classrooms. And so I'm going to talk about my own efforts to bridge from cognitive science to education, focusing on this basic learning process of comparison and how it can be harnessed to improve learning. And that's going to be especially about mathematics learning in schools. And one thing that I just am a key advocate for is that you cannot do this alone, that no one person has sufficient expertise to do this kind of bridging work. And so for myself, my key collaborator throughout my career has been John Starr, who's a mathematics education researcher. And for those of you who are new, just emerging scholars, I also like to point out that John Starr and I have never been at the same institution. He introduced himself to me when we were both in graduate school, which was really a very long time ago now. And we gradually built a research program together, really now that's spanned decades. And so I just really encourage you to reach out and find people and work together. Okay, so comparison. Well, I'm going to do my quick little why we care about comparison to a group of people who mostly already do, but just to remind you of how much we learn and use comparison. And I start off with this everyday example of making shopping decisions. Perhaps this year you have spent more time doing online shopping, and okay, maybe I want to get a new iPhone, and I can click on this really handy compare button on many shopping websites, and that's going to pull up multiple different phones. It's going to tell me different things about them, and that's going to help me start to notice things like, gosh, do I care if it's water resistant? Because they vary in that. So this comparison of phones helps me make smarter choices for purchasing. It's also something babies do. So we're doing it as adults. They're doing it as babies. It's helping them learn categories like cat versus dog. It's helping them learn words like fruit. So it's really ubiquitous. And because of this ubiquitousness, it's really been considered a core learning process. So I saw Dedri here on the call, so that learners compare two examples, and by doing so come to understand the underlying structure common to both. And Rob Goldstone claiming that comparison is one of the most integral components of human thought. In case you need a little more convincing, in addition to these examples, there's a strong empirical literature behind this. So we know that comparing multiple examples supports learning across many topics. There's a really nice meta-analysis done by Alfieri and colleagues. For example, it promotes, I just pick examples of such wide range. So perceptual learning in adults, transfer of negotiation principles in adults, category learning in language in preschoolers, and spatial categories in infants. I mean, I think that's kind of a remarkable span. But at the time of this research that we began this, there was no research with school-age children and nothing on mathematics learning. So why the heck did we decide to study it for supporting math learning? Well, we noticed an overlap. If you look at best practice recommendations in mathematics instruction, they really talk about and support the use of comparison. And that comes from sharing and comparing solution strategies as being core to reform pedagogy in lots of different countries around the world. And that's largely based on the fact that it's something that expert teachers do in a variety of countries. Here is a rare example from a Japanese textbook of two different students' solutions, just to give you a sense of what that might look like. But this leaves the question, okay, well, you know, expert teachers do a whole bunch of things that are really useful. Is comparison really key? And because at the time, we just didn't have any empirical evidence that comparison supported students' math learning. It raised the need for guidelines for how to use comparison effectively in mathematics learning. And so our research goal was, how can comparison support learning of school mathematics within classroom settings? And we started this with a short-term researcher-led studies. I decided to find out when we started this, and it was in 2005. So it has been a while. And then we transitioned to year-long teacher-led studies. In most of this work, although not all, we've focused on algebra learning. And we've done that in large part because proficiency in algebra is really critical to academic, economic, and life success. We know that success in algebra is necessary for access to higher mathematics and many job opportunities. And we also know that students have pervasive difficulties with algebra. I'm pulling here data from the US. We see this in other countries as well. Here's an example that only 31% of American 8th graders were able to find an equation of a line that passes through a given point and with a negative slope, a fairly straightforward algebraic problem that not near enough American 8th graders were able to solve. So with this in mind, we started, as I mentioned, back in 2005, and went for a number of years on these 5 short-term researcher-led studies. And in these initial studies, our approach was to, and I do want to highlight this approach because it was, for me at least at the time, it was quite a new approach to doing work for, as a cognitive psychologist who was trained to pull kids out of the classroom and do one-on-one stuff with them. Was to redesign 2 to 3 math lessons on a particular topic like equation solving, implement that during students' mathematics classes by researchers, but importantly, we maintained an experimental design in that work. And we had to figure out what all students were going to do. And so we had them study and discuss worked examples with a partner. Here, again, we really drew heavily on the cognitive science research that there's advantages to using worked examples, to generating explanations, and to doing peer collaboration. So all kids did that. And then we worked to figure out very carefully how to support comparison. And that's where we use the cognitive science literature really carefully. You can see citations here at the below, and so obviously work by Dedry Gentner and Lindsay Richland have been very influential in how we've done this work. So we present worked examples illustrating 2 strategies simultaneously. The simultaneous is important. We use spatial cues, common language, and those worked examples to facilitate comparison. We ask specific explanation prompts to focus attention on key aspects. There's nice work that those specific explanation prompts improve the effectiveness of comparison. And also we provide some direct instruction to supplement learners' comparison based on evidence of the importance of supplementing with direct instruction. I want to point out, and this is a constant struggle with us, this presenting things in worked examples. As cognitive scientists, you're like, of course, worked examples are great. Not, of course, when you're talking to math ed world, they really do not like worked examples, and this causes some grief sometimes. And we can talk sometime about how we navigate that. There are ways to make that better and worse ways to talk about that to make it acceptable in the math ed research community. By the way, teachers never have a problem with worked examples. They're not where we get pushback. Okay, so what's the compare condition? This is an example from the very first comparison study we did. You have Mandy's solution and you have Erica's solution. They both solve the same problem. They use 2 different strategies. There are explanation prompts asking you to reflect on them each and compare them. In the sequential condition, you also see Mandy's solution and Erica's solution. You see them on separate pages, on isomorphic problems, and you're asked questions that ask you to reflect, but only to reflect on the individual. So here, it's always important to note in these studies, in these initial studies, everyone got exposed to multiple strategies. That's not what we manipulated. We manipulated whether there was support for comparing them. Turning to the outcomes we considered, again, if you are interested in bridging to education, you really need to have multiple outcomes. And that's another talk about agreeing on these outcomes and which outcomes are the best and which ones are the right way to measure. But these are three that we've settled on as being really important that lots of consensus documents promote. So the first is straightforward procedural knowledge. Knowledge of procedures, the steps, actions that you take to accomplish a goal. And we include the ability to adapt a known procedure to unfamiliar problem features. Then we have conceptual knowledge, knowledge of concepts, abstract general principles. And then the thing that's less familiar in the cognitive science literature is procedural flexibility. And this is knowledge of multiple procedures, as well as the ability to choose the most appropriate one based on specific problem features. And we focus on procedural flexibility for two reasons. One, it supports efficient problem solving, greater accuracy solving novel problems, greater conceptual knowledge. It's also a salient characteristic of experts in mathematics. Experts are very flexible. So what might this look like when you try to measure it? Procedural knowledge is the easiest thing. You look at their accuracy solving equations if you're studying equation solving. Conceptual knowledge, knowledge of concepts like equivalence, like terms, composite variables, and procedural flexibility. In our early work, we always used two measures of procedural flexibility. There was flexible use, which was use of more efficient solution strategies on procedural knowledge assessment. So on that top measure, did you use the most efficient method or more efficient methods? And then we had a separate independent measure of flexible knowledge. And that's what this looked like. So part of it was your knowledge of multiple strategies. So if I prompt you, can you solve it in more than one way? And then also, can I show you a novel or maybe just not super familiar solution step? What do you think about it? What's your evaluation of that strategy? So we kind of consistently measure all three of these things in all of our studies. So in the very first study, we did a simple compare versus sequential condition. I say simple, but anyway, we had 70 7th grade students. That's 12 to, all this work was done in the US. That's 12 to 13-year-old kids. In the US, these students had some prior instruction on solving equations using one method. And I'm going to come back to that. That turned out to be important. Although, yeah, the research design, pre-test, intervention, post-test design, random assignment. The compare condition, I showed you sample materials. You compare and contrast alternative correct strategies for equation solving. Sequential condition, you study those same strategies. Everyone gets multiple strategies, but you do them one at a time. Looking at results, first, in this first study, we used gain scores and then we moved away from them. But for this first study, I'm going to be showing you gain scores. So the y-axis is post minus pre-test score, the gain. And the dark bars are the compare condition and the light bars are the sequential condition. And here you can see both familiar problems on the left and novel problems on the right, meaning they had a novel problem feature. Students in the compare condition had greater gains than students in the sequential condition. We did not in this first study see differences in gains in conceptual knowledge. There was just no effective condition. Conceptual knowledge is really hard to measure reliably. This is a persistent issue, not just for us, for other people too. So we'll see, sometimes we get it, but getting the reliable measure is like half of the battle. Oh, it's probably more than half. And then procedural flexibility is we did see differences. So this is flexible knowledge. So this is kind of when you are prompted and you evaluate it, the compare condition had greater gains in flexible knowledge. And they had more flexible use. So they were more likely to use the most efficient method when they solved problems. You can see 17% of problems versus 10% of problems. It's not like there's like rampant use of the more efficient strategies, but we do see an increase, and it's a pretty substantial one. Okay, so with this really encouraging news in mind, as cognitive scientists, we stepped back and said, okay, why is comparing correct strategies aiding learning? And in this work, I draw really heavily on Deirdre Gentner's analogical learning framework. And that's where the students were familiar with one of the methods because of their prior instructional history. They were comparing this new method to a known method, identifying similarities and differences with the known method. I think about this as being a structure mapping process. And we did indeed see, we coded, the students would explain out loud and then they would record their explanation. They would talk with a partner and then record an explanation, and we coded all of those explanations in our early work. And so the frequency of comparative explanations was a predictor of learning. And this really made us wonder, is the familiarity with one of the methods important to comparison? This is a really important question for a teacher to know the answer to, and I think theoretically for us to understand the process. And so in our second study, we wanted to know if children with different levels of prior knowledge benefit equally from comparing solution strategies. And here we had a much bigger sample, because when you're looking at some individual differences, you need a lot more kids. So we had, oh, well, it's telling me this meeting will end in 10 minutes. Scores, there's like state test scores. And that wasn't important. They did not interact with condition. It was your use of algebra that was predictive as an important interaction. We see the same thing with flexibility. So you're more flexible if you didn't attempt algebra in the sequential condition, and more flexible in the compare condition for the most part if you had some attempt of algebra. So I think it's really important to highlight that general math ability, that's not what this is about. It's familiarity with one of the solution methods, which is what influenced learning from comparison. And I think that a structure mapping analogical learning framework would suggest this implication. So for students without prior knowledge of algebraic strategies, sequential study produced fewer signs of confusion, and it was best for procedural knowledge. They got through more materials. I didn't tell you the data on that, but we analyzed what was happening in their student work. And then this sequential study of examples was best for procedural and conceptual knowledge and flexibility. But for students with prior knowledge of algebraic strategies, comparison was best. Okay, is there, I'm going to have a better transition point in one more second. So the question is, should delaying strategies be delayed? We know from work by Deirdre and others that adults learn more from comparing two unfamiliar examples and studying the examples one at a time. It's possible to learn from comparing two unfamiliar examples. And so we did a follow-up study that found that even novices learned more from comparing strategies if they were given adequate instructional supports. So in this high support context, delaying comparison of methods reduced procedural flexibility for all students. So this suggests we should use comparison, and we should use it early on, but we need more supports for it to be successful early. Another interesting thing that we started to notice is you really have to make a lot of decisions about what you're comparing. So we started off with what happens in mathematics education most often, which is kids are comparing methods or strategies for solving the same problem. But those of you in the cognitive science literature probably noticed that's actually not what's usually compared in cognitive science. Usually you're comparing problems solved with the same method. So like if you think about Dunker's radiation problem, you're providing the same solution in two stories with different cover stories and prompting for comparison. You're greatly increasing spontaneous transfer of the solution, and kind of classic work by Gick and Holyoke, Cantrombone. And so this got us really interested. Well, what about this kind of comparison for mathematics? And so we created 3 comparison conditions. At the top, you have Mary's solution to this equation. And the first conditions, just like we had done in our first couple studies, where you have one problem and you're solving it in 2 different ways. We really thought about 2 potential ways to think about, the classic Dunker radiation problem research in mathematics. One is that you're comparing problem types. That there are some dissimilarities in surface features. So they're 2 different problem types, but they're saved and basically solved in the same way. Mary's problem becomes an isomorph to Bill's problem after you implement a step. And then alternatively to equivalent problems. So we have 2 similar problems solved in the same way. Sometimes I take a vote about which will be most effective. I'm just going to reveal it. Some of you know this work because we did it a while ago. So we found that the intuition in mathematics literature about what expert teachers do, probably not surprisingly, was what was more effective. So comparing 2 different ways to solve the same problem. Oops, I'm going to work on muting. Sorry, I don't have these.
Acabou do... Não, então tudo bem. É que eu não quero mais café, eu só queria... Hã? É que eu passo não, eu só queria esquentar.
Actually, I see lots of people, and I'm sorry, I don't have this. Oh, yeah, it's not, I'm going to make, now that Margarita is here, I'm going to make her a co-host.
Thanks, I will take care of this.
Okay, I couldn't do it till you were here. Okay, awesome. All right, so we found that comparing methods or comparing strategies, that led to more flexible knowledge and greater conceptual knowledge than comparing problems, either equivalent problems or problem types. And there were no differences on the other measures, but this suggested to us from across our short-term researcher-led studies that what is compared matters. For math problem solving, it seems particularly effective to compare a familiar strategy to to compare a familiar example to an unfamiliar example, and to compare solution strategies. And that comparing strategies can promote learning at multiple phases of instruction. If it is supported well, carefully designed visual presentation of multiple strategies, if it's early, but when it's early in instruction, students need strong support to engage in comparison effectively, including sufficient time. Waiting to compare strategies for too long reduces students' procedural flexibility. So later in instruction, students still benefit from comparison and they can do it more effectively on their own. Okay. So any questions on this kind of side of things before I transition to talking about our teacher-led work? I'm happy to take them at the end as well. All right, I'm going to keep going. If you think of something, ask me at the end. All right, so as we think about, and as Margarita mentioned in her introduction, we have had some success in, what are the implications of cognitive science for the classroom? And here in the United States, the US Department of Education, through its research arm, puts out these educator practice guides that are evidence-based practices. And this guide on improving mathematical problem solving in grades 4 through 8, their 4th recommendation, you'll see the 2nd line here of provide opportunities for students to compare multiple strategies and worked examples, is heavily influenced by our research. And so this is one way to have reached teachers. Similarly, they put out a practice guide on teaching strategies for improving algebra knowledge in middle and high school students. John Starr helped lead this effort. And recommendation 3 is to teach students to intentionally choose from alternative algebraic strategies when solving problems. And again, this recommendation is centered around the research that I have just talked about. So this is great, but we knew it wasn't. If you really want to impact classrooms, even if you can get in these national guides, it's very unlikely to be enough. We really felt that we needed to help teachers learn to use comparison effectively. We based that on the fact that, for example, high quality implementation of a comparison approach occurred in only 12% of lessons that even incorporated multiple strategies. And we know that comparing strategies is rarely done in textbook lessons on algebra. So I've done some analyses of both US and Japanese textbooks. And we found that only 1% of worked examples in the algebra lessons included multiple strategies for solving the same problem. And when they did happen, comparison wasn't supported. I showed you briefly an example from a Japanese textbook before. Here's one from an American textbook, Big Ideas, Algebra I. Here, they show two ways to solve method 1 and method 2, like methods we show our students, but there is really limited support for comparison, and it's never explicitly suggested to the students. So it's just what's out there is just not enough. And so we were, and this by we, this is work that as a cognitive scientist, I could never have done this work, led this work by myself. This is where John Starr was particularly instrumental in developing a supplemental Algebra I curriculum and professional development for teachers to integrate what we call comparison and explanation of multiple strategies in their classrooms. After we did this, we evaluated its promise in a randomized controlled trial. So this curriculum is to be used in addition to existing Algebra I curriculum. It covers topics such as solving linear equations, functions and graphing linear equations, solving systems of equations, polynomials, and factoring. This is like bread and butter Algebra I content in the US, typically taught in 9th grade. We used the cognitive science literature, especially Lindsley Richland's work, guiding our support of comparison. So we presented 2 different strategies for solving the same problem. We presented them as student solutions to encourage critical reflection. So this is one way where the worked example being from a student perspective, promoting reflection, we both believe in it and also is more comfortable in the math education research literature. We make both examples visible and clear. They're presented side by side. They get explanation prompts for students to understand each strategy individually. That emerged from our early work that's if you jump into comparison right away, those groups didn't learn as much in general. So we need the students who took the time to learn each strategy first learned more, and they compare strategies to identify pros and cons. And we also include a lesson summary highlighting a key point of the comparison. We observed that teachers were sometimes skipping this kind of lesson closure, so we tried to build in supports. I think something that was really cool about this work is that new types of comparison emerged when we sat down and tried to map out using comparison to support algebra learning, and we involved teachers in that process. I will say that we tried to secure funding to study the effectiveness of each type of comparison individually. Some of these already had been studied, but some had not, but we were never successful in convincing funders. So I'm going to tell you about them as a batch. Well, we have this one form of comparing correct strategies, which we had already documented as being effective, which is what we call which is better. There are 2 correct strategies. One's going to be more efficient on particular problems. So you're learning kind of the if you're a if-then person, you're learning the if statements. When do we use this? But another new type emerged, which we call why does it work? So you can see here, it's Morgan's is a great example. Morgan's cross multiplication way. Okay, it's an efficient strategy that most teachers and textbooks teach, but it's like pretty opaque why it works. And so we compare it to kind of what we call the long drawn out version that helps you understand why the efficient strategy works. And so this, I think, is a very promising form of comparison. We have anecdotal, I guess, evidence to suggest that this type of comparison is pretty effective. We added, and this does have a research literature behind it, which is correct comparisons. So here you're seeing two strategies, one's correct, one's not correct. You're asked to figure out which one is incorrect and why. We have a new kind of comparing problems. How do they differ? These problems are pretty infrequent, but they happen occasionally because it's really useful sometimes. Here as an example where there's a positive versus a negative coefficient, where the problem features, it's helping you understand key things about problem features. So we have these occasionally when they're helpful, when they seem helpful. Okay, so our initial CEMS curriculum had 140 comparison examples covering all units in Algebra I. It was a really big effort. We developed professional development that was 1 week for 35 hours during the summer. During the school year, teachers were asked to use our materials at least once per week. We gave a lot of teacher autonomy. We asked them which materials to use and when to use them. There was never a researcher present in these classrooms. We had a set of Algebra I teachers from Massachusetts that were randomly assigned to condition. We did have attrition after random assignment, which is a headache, but it happens because that's the real world. 39 teachers and their 781 students used our comparison materials, and 29 teachers and their 586 students used their existing approach. So it was a business as usual control condition. We used a standardized commercial algebra test, the Acuity algebra. We used our own researcher designed assessment of algebra knowledge that had conceptual knowledge, procedural flexibility. Teachers administered both of these assessments at the beginning and the end of the school year. And it was really depressing. At the end of the school year, there was no effective condition on any outcome measure. I am not showing you the data. The means are on top of each other. It's depressing to look at. The two students in the two groups performed the same. But as we dug in, there was large variation in how frequently teachers actually used our materials, and they were using them much, much less often than we had requested. So we did a dosage measure, which was how often they used our materials times the average length of the time they used it, because they were videotaping themselves. And average dosage was 140 minutes in the entire school year, which is less than 4% of math instructional time. So it's pretty hard to move the needle on student achievement when you're getting less than 4% of math instructional time. And we did see that increased dosage was associated with increased procedural knowledge. And so this glimmer of hope and lots of ideas about what had gone wrong allowed us to secure funding to revise our curriculum. We now call it comparison and discussion of multiple strategies. Because one thing we learned is that when we said explain, teachers thought as long as they explained it, it was fine, but we didn't mean teacher explanation, we meant student explanation. So we use the word discuss, and we provide a lot more support for having high quality class discussions. And we increase dosage by specifying what materials to use when. So we just decided to focus in on 5 units with 40 comparison examples to be used in most daily lessons during those units. You can see here for each lesson, we suggest use this comparison, it's this type, use it when in the lesson. So we did mapping for them. I think the thing is we really believe deeply in treating teachers as professionals. But the problem is they are professionals with vanishingly little planning time. And so they just did not have the time to plan. So we just needed to do that work for them. We integrated a cast of 5 more diverse hypothetical students. So when we revised our materials. And then we did a lot to leverage the power of discussion. We increased support for explanation and class discussion. We developed an instructional routine and materials for what we called a 20-minute CDM-esque cycle. where you have the compare phase and a discuss phase. And this, you prepare to compare, you make comparisons, you prepare to discuss, you discuss connections, you think about big ideas. We provided materials to support discussion. We have this graphic organizer that supports a think, pair, share routine, which was really, really helpful for these high school teachers who have, for the most part, high school math teachers have zero routines for supporting partner work and student discussion. Students summarizing the big ideas in their own words, teacher guides. We increased professional development. So in addition to the summer, after each unit, an individual researcher, we had an individual meeting with a researcher and teachers where we provided personal feedback on videotape lessons and helped them plan for the next unit. This is just a side where we would say, like, here, you did this well. Now let's build on this strength and push you to do this. This is not sustainable, but it is useful. We've been thinking about how to make this more sustainable, but this is what we did because we wanted to really do it this time. All right. So in phase 3, we asked teachers to use our materials several times a week during the 5 units of instruction. Again, there was no researcher present during instruction, but after each unit, we met individually with a researcher for feedback and to plan. We hired videographers, if you're interested. That works pretty well. That like worked at the school usually. The data was collected. This time we were wise enough to add unit assessments at the beginning and end of the 5 units instead of just a beginning end of school year. Most treatment and control teachers, actually especially control teachers, only got through the four of those units. The overall assessment at the beginning and end of the school year, and the videos of instruction, 2 to 3 videos per unit. They were done by videographers at the school, someone in the community. We had 2 waves of data collection in phase 3. Wave 1 was our pilot year. We had 9 treatment teachers who used our CDMS approach with over 350 students. Most were in 9th grade. And then wave 2 was our test year. We had 16 treatment teachers, 7 of whom participated in the pilot year, and their 550 students, and 13 control teachers with 498 students. I'm going to say here, the recruitment of teachers, we recruited the control teachers after the treatment teachers, so there is not random assignment happening in this study. The schools were in suburban and rural Massachusetts and New Hampshire and served predominantly white middle-class students, which is an important note. And most of the students were in 9th grade. There was 1 8th grade classroom per condition where they were doing Algebra I a year early. So in our test year, really nice dosage. They used a median, or pretty good. Used a median of 28 of our 40 comparison examples, spending an average of 17.4 minutes on each, which was a really substantial improvement from our phase 2 dosage. We really only had 2 teachers who were using less than 24 examples. So most teachers were doing this pretty often and regularly as we had asked. Looking at the presence of key CDMS instructional components, you can see in our treatment lessons, of course, they're exposing multiple strategies side by side because that's in our materials. They usually were doing sustained comparison, sustained partner work, sustained whole class discussion. When these numbers aren't 100%, it's because they did them, but they did them really quickly. They didn't do a sustained version. And just to give you a sense of what's happening in algebra classrooms without our materials, they do get some exposure. About 21% of the lessons included multiple strategies, but not a ton. They tended to be side by side when, if they were there, but they were not doing sustained comparison. They're doing some group work, not a lot of sustained, and there's like virtually no sustained whole class discussion in these high school classrooms. Well, you probably don't. Anyways, if I'm talking to a group of people who work with elementary and middle school math teachers, like high school teachers are different. They're trained differently in the United States. They usually have a math degree, so that math knowledge isn't their problem. It's the pedagogy side that they have a lot less experience in. I think for time, I'm not going to go through this, but we did look at the instructional quality coding of the treatment lessons. They were doing some making sense of procedures. Supporting procedural flexibility, these were rated on a 1 to 4 point scale by expert teachers who weren't on the project. Teachers were doing decent questioning, student responses were pretty good. Opportunities for whole class interaction was still a weakness. Even with all the support we provided, it was not enough to get most of the teachers doing really good back and forth discussion, like you saw in the video clip. Okay, so what did we find? In this first paper that's just come out, we did find on Unit 1 that students' performance, the treatment students outperformed the control group on the Unit 1 post-test, and this was particularly true on the flexibility items. So that was really encouraging. Looking at the overall assessment, although the means are in the expected direction, once you control for school level demographic differences, because I noted there's not random assignment here, there was the effect for treatment is actually overall is not significant. It is marginal on the procedural flexibility items. So this was definitely disappointing. We do see some effective dosage on the overall assessment. So high dosage, the number of minutes across the school years using our materials did predict overall post-test scores. So there is evidence, again, if we can get teachers to do this more, the students do benefit. So to summarize, comparison and discussion of multiple strategies does support mathematics learning. There's really consistent benefits of comparison when used intensively for short periods of time, especially comparing correct solution strategies when have some prior domain knowledge. Teachers need strong support to use explicit comparison of multiple strategies, collaborative group work, and high quality discussions. Providing materials and routines has been really key to this work. We did not provide enough routines in our phase 2 work. And that professional development, including feedback, has been key to be effective. We have been pursuing funding to look at continued late stage development research. You'll see it's just, I mean, we've worked so hard and we've moved the needle some, but we have not had these big impacts that we would love to, that we would predict. We have some anecdotal evidence that we're improving student and teacher beliefs. And so we are actually also interested in measuring and documenting that. So I'm just going to end to this group of cognitive scientists with some lessons I've learned from doing this work, trying to bridge between cognitive science and the classroom. It's a long journey. I've been doing this now for 15 years, and really that you need good collaborators from related disciplines, and ones that you like and get along with well. That's important because we talk a lot. Noticing overlap in cognitive science, and in my case, math education research, led to our initial idea to focus on comparison. So looking at overlaps between what you're doing and maybe is being recommended in a discipline of interest, but isn't well enough understood, was productive. Conducting research in classrooms from the very beginning was very useful to having a practical approach. We had to make a lot of decisions up front, because, you know, am I going to control for time on tasks or number of problems studied? Well, you know what? When you're in classrooms, you control for time on task because they all have the same length of class. That's just a small example. I needed to figure out how am I getting at students talking to each other? Oh, partner work, that's a good way to do that. Okay. Thinking about theory to practice, attending to theory guided us to consider the importance of prior knowledge. That was really useful. We used it a lot in how we support comparison and discussion. On the reverse, we found these different types of comparison arose during materials development that weren't systematically considered in theories of learning from comparison. Also, the lesson that what we first considered a relatively small change to teacher practice turned out to be a bigger change than we anticipated. We began with lots of teacher autonomy and moved to providing lots more guidance and routines. I would say up front that conducting a randomized control trial immediately after materials development was really a crazy idea, frankly. NSF funded it in this enthusiasm for RCTs that happened about a decade ago, but lots of studies were like ours. but they just did not, that rapid switch to an RCT did not show benefits to student learning. And so now we focus much more on teacher implementations and perspectives now. And so I just want to acknowledge my collaborators. We have websites. We have a website, teacher-facing website. We have a researcher-facing website. You can get all of our materials, all of our assessments. We are happy to share them, happy to have you use them. And thanks very much. I'm happy to answer questions.